joining us from Princeton University, where he's the Frederick D. Petrie Professor of Ecology, Ecology and Evolutionary Biology. So, and he also got his PhD at Stanford University in biology. And at Princeton, he does a lot of amazing work. But in general, he focuses on problems of global change with an emphasis on interactions between the biosphere, greenhouse gases, and climate. So he does a lot of great research that's really helping us solve solutions to climate change, the dynamics of forests, and also just the whole relationship between biosphere and ecosystem function. Um, he does many great things. He's also the co-director of the Carbon Mitigation Initiative. He is on the board of the Environmental Defense Fund, which is very, very exciting. He's also the founder and the chairman of the board of Climate Central, which is a great nonprofit media organization. So look it up. I was looking at it right before here. It's really, really great. So yeah, he has many, many great awards. Some of his awards include the David Starr Jordan Prize, the Jordan Mercer and Robert Parker Awards of the ESA, the Ecological Society of America, and he's also elected to the American Academy of Sciences, Arts and Sciences, and also the U.S. National Academy of Sciences. So this is going to be great. I know there's so much that he's going to be talking about today. He's developed some land surface models that I personally work on, that a lot of us here at the lab that we all have worked on. So very, very excited to hear his talk. So welcome, Stephen.
Well, it's always great to be here. The last time I was here, I was actually talking on energy technology. And there were a bunch of elderly physicists in the room who were wearing suits and ties. And so I didn't know how to dress when I came here this morning. And so as the resident old guy now, I want to, get rid of this and talk a little bit about land surface modeling. And this is really a story. For me, it's been an effort that extends over 2 decades, more like 3 now. And I want to talk a little bit about the underpinnings of what it is that some of the land modeling groups, particularly the ones focusing on vegetation, do and why they do it. And why the phrase modeling the terrestrial biosphere isn't just a silly phrase, all right? It's easy to say modeling the terrestrial biosphere, but if you think about it, if it weren't for there being a global warming crisis and the fact that the terrestrial ecosystems are such a big piece of the climate system, we probably wouldn't be ready to model the terrestrial biosphere in anger for 100 years, right? Something like that, right? Policymakers need the best available information based on the best available science, and the problem unfortunately doesn't wait. But nonetheless, this is an area in which there is, I think, the possibility that the science is developing to meet the task. So I'm going to give you a particular take on this that I hope will resonate if you're an ecologist or if you're a statistical physicist, right? So the first thing about the terrestrial biosphere. So I'm going to talk about scaling from tissue to individual to population to community to ecosystem. And if you're a scientist in most other fields, there are really 2 things you need to have a proper theory. The first is there have to be a set of phenomena that are sufficiently regular that there probably is a simple explanation within grasp. There are plenty of things that are too complicated to understand in every discipline. And in this case, with vegetation, we all know that you can train an undergraduate in a month to be thrown out of an airplane anywhere in the world, land on the ground, look up at the vegetation, and tell you in pretty good detail what the climate is, all right? They can tell you the nitrogen mineralization rate. They can tell you the distribution of species abundances. They can tell you all kinds of things. They can tell you the successional age usually, all right? And so this, to me, has always been the flag that's out there that says, yeah, this enterprise is not just silly. There's something really simple and deterministic at root here. Something that's going to have a laminar flow explanation, not 200 years in when we understand turbulence, right? So that's one. Postpone. Huh? So that's the first thing. So if you have a phenomenon like that, and you have some understanding of mechanism, and mechanism means that you have some understanding of the governing dynamics and rules and constraints at lower levels of organization, then a theory is going to be a way to scale correctly. That's the sort of historic route. And so I want to talk about scaling. So my career has been all about scaling. I'm going to talk about two different approximations in ecosystem models. The first is this thing that I named the ED approximation on a run because I was sick of cool names like COBRA, and that stands for ecosystem demography. And a second one called the PPA approximation. And these are used all over the place, including by a lot of people here in the room. And then I want to talk about three different applications, but I'll probably only get to the first two because I'm going to run out of time. All right? The first one is the statement that a prediction, really, that nitrogen shortage won't stop the carbon sink. So it's, running out of nitrogen isn't going to stop the global carbon sink, which for me is extremely good news. Now, that's a prediction. I don't know if it's correct, but I think it might be. And the second one is the cause of the mysterious rainforest power law. Right? And that's actually a data analysis and model that I think is the correct answer. And then there's a third one that has to do with the controls of the deciduous evergreen balance on the planet that I probably won't get to, but maybe I will. Okay, so for me, the underpinnings of theoretical ecology trace back to ecology's heroic theoretical age, where people just were making up models of ideas all the time. And the people I've got here are Bob May, who's now Lord Robert May, Robert MacArthur, who tragically died when he was about 40, and this is Cy Levin, a good friend of mine. And these people all made up models of ideas that weren't intended to be tested, right, in any way that we would understand, right? And this is often the case when a field is in its heroic phase. And what happens then is that it either kind of fizzles out because these models don't lead anywhere they never can be used in anger, all right? They're always tested at a distance sort of with binoculars, right? Or sometimes they lead to what I think of as the science to engineering transition, where you have models that work for the right reason, that are simple enough to be understood, and that people start to use simply because they're better than what they had before. Like the transition when, in physics, Newtonian mechanics was used to design bridges because they were better than the received wisdom from your guild, right? Nobody necessarily cared whether or not the explanations were beautiful, though they were, right? But it was just that they worked better. And I think that demonstrably, ecology has passed this transition in a couple of places. And happily, one of them is in forest modeling. So I'll make this case now. So this is a Jabberwock 4A model. This is from Hank Schugert's book, right? And these things have been going since practically the dawn of the computer age, in which you simulate the fate of every individual plant through its life cycle. I'll talk a little bit more about that later. Now, why is this good? So I want to make a claim that these models have passed the transition. They're demonstrably used all over the world to manage timber, and I'll show you a couple of examples for that, just because they work. And they're useful. This is useful here because I want to ask the question, what is wood? And the answer is most of the biosphere's carbon either is or used to be wood. All right? Actually, what used to be woody tissue. It's because the stuff's recalcitrant and because it weighs a lot and it piles up in the ground and it's long-lived, right? So if you're going to get one thing right, you better get forests right if you're building a carbon cycle model in particular. And the second thing that's interesting is that wood is a weapon that trees use to kill their neighbors and their neighbors' children. Right? They use it, the world would be far more productive if trees didn't waste energy on wood. Wood is a game theoretic weapon, and you should think of its purpose as aggressive, as a defensive and offensive weapon. And so it needs to be modeled as a weapon in the same way that you can't model the economy of North Korea as a productive state that produces, cell phones and food for people. You have to, if you want to understand something like this, most of the biosphere's carbon, you better include its function, and its function is a weapon. And these gap models are all about that. That's why they work. Big trees shade taller, big trees shade smaller trees, and that's why gaps need to form for the forest to regenerate. Okay. Now, I worked on these for a long time with all kinds of collaborators. This is a model that we built in the 1980s called Sortie. And Sortie, this is a little picture of a state of Sortie at a particular time. Each one of those objects is a tree. The purple ones are American beeches. The green ones are eastern hemlocks. That's a yellow birch. There are a bunch of different species in there. All the little ones are little teedy trees. And these things are growing up, falling over, gathering resources, dying and giving birth, and shading each other out in much the same way that a forest does. If you look at it, it's what it does. And these things are parameterized from a bunch of functions that you go out and gather in the field. In this case, it was a relatively simple set of functions. I've got one here for just a purely light-limited forest, but we did this work for a lot of different kinds of limitation. There's a function that gives the number of births produced at a distance from an adult as a function of an adult size that we develop statistical sampling techniques to produce, and you can go and do it in a couple of weeks' time for all the species in a forest. There are functions that determine the resources available to an individual given the individuals around it. In this case, this is a shading algorithm, right? It's like a ray tracing algorithm. There's a radiation code. But you can also do this below ground. Then there's a growth function. Growth is a function of resources that you get from regressions, from measurements. And then there's a probability of mortality. In this case, given recent radial growth history, which is a good proxy indicator for the carbon status of a plant and its probability of starving to death in the understory. So from these, you can predict the death, birth, and growth of all individuals in a forest, and there can be millions of these things, and you can use them to predict the future of the forest and its dynamics through time for thousands of years. And the amazing thing is that we and many others, when we went and did this sort of thing, we did this sortie first in a Connecticut forest. We never went to an old growth forest. We worked along roadsides and wherever we could. And then we predicted the old growth in this forest. And these are predictions versus all the remaining data from old growth for all these different species. And you see, we really just do a remarkably good job. There's in fact only one statistically significant error for sugar maple, where the actual values are higher than the predicted. And the reason for that is that sugar maple has caught a recent disease. And the sugar maples that are old out there were ones that had gone through their youth without having to catch the disease. All right? So we actually made that prediction. That prediction is wrong for the right reason. So this is why, in fact, these things have exploded all over the place. And I have one example for you here of how these things are used now in anger. So close to 10 years ago now, the largest insect outbreak in history happened and killed an area of roughly the size of New York State in British Columbia. It's an explosion of this mountain pine beetle, which you know is a climate, global warming exacerbated pest. And it knocked out the lodgepole pine over this humongous region that was wholly dependent on the logging industry that came from it. So the Canadian government faced 15 years in which they could do salvage logging. They thought they could get marketable pine trees again in 35 to 50. And then there was a 20-year valley of death where they were going to have to depopulate an area the size of New York State. Right? This is a really serious problem for them. So what to do about it? Well, fortunately, David Coates and Charlie Canham had built sortie models of I always make fun of them for this because it's like their mother dressed them the same when they were born. Even the clothes. Anyway, so these guys had built a sortie models. They had what they thought was a good dynamical understanding of how this forest would respond to sort of a novel initial condition. And what the inventory work showed was that, there was a sub-canopy of two species, interior spruce and subalpine fir, that were pretty common in lots of different stands. And so, and although these things typically don't form canopies, they thought, you know, we ought to be able to predict whether or not, if you protected stands that were particularly rich in this subcanopy from salvage logging, so they don't get all chewed up by the skidders, then maybe we could sustain the economy through this valley of death. And so they made the prediction, and go to the top here. This is like a two-hand mouse for me. 4 hours. Okay, yeah. So they made the prediction. They said, yeah, it's going to work. And then all of the industries that jumped in and said, we got to build one of them models too. And they did it really fast because all the methods existed. They had the models they all use models like this. Everybody uses these models to manage their timber, but they were specific models for lodgepole pine. So they had to build the right models, and they did. And as is true of a mature science, when everybody tunes the models up independently, they all get the same answer. When it's not mature and you all tune them up, the answers diverge, right? I mean, look at the CMIP5 or system modeling to see what I mean, right? And so as a result, British Columbia actually passed a law based on what this model said about how you're allowed to salvage log. And since then, they've monitored it intensively, and it's working absolutely perfectly. So in this case, you know, gap modeling saved the town, right? All right, so I want to talk about, so we start from the idea that because of Hank Sugar and all these people, we've actually got the legacy of a set of models that appear to do the scaling, at least from individuals or parts of individuals up through these sort of stand scales correctly, at least accurately, and also predict the responses of the system to novel conditions. And now the question is, well, what are we going to do about the globe, all right? Given that most of the carbon molecules in the biosphere, terrestrial biosphere, used to be wood. And the problem is that there are 3 trillion canopy trees, literally, and way more than that understory trees. And you can't simulate them all. So what are you going to do? And the answer is, for the same reason that we use the Navier-Stokes equations rather than stochastic billiard ball models of atoms, of molecules in the atmosphere, to simulate atmospheric dynamics, we need a set of macroscopic equations that predict the means for the right reason. Now, what do I mean by that? Well, let's suppose what we want to do is to calculate the time evolution of the mean population density of species I at size S and time t. So this would be a tree of particular, say, diameter or height or something. Size can be a vector. A set of characteristic I is a species thing. And we want to know at a particular time how many of these, what's the density of those, and rather than simulate them all. So what would we do to calculate this density? What does it even mean in this context? Well, here's a gap model. It's gone the wrong way. Let's see, here's a gap model. And this is actually a fancy one. You're looking down on a bunch of trees. There's 2 species here. One is a hemlock, one is a white pine. They seem to be moving around a bit, and it's because they're doing phototropism. They're searching for the sunshine in gaps. And this is actually a realistic level of phototropism, and they're forming gaps and regenerating and doing things. This is actually a simulation that works well, right? So I've thrown a small box on the ground, and I want to count at time t, at a particular time frame, is there not a species of a particular size in that gap, in that little box, okay? And if the box is small enough, there will either be 0 or 1. So it's a Bernoulli random variable, right? So at a particular time, I wait 100 years and I say, there's nobody in there, that's a 0, okay? And maybe at some point you'll see in this simulation there's exactly 1 tree who's rooted in that box, right? So you have these Bernoulli random variables. And then if you do this a bazillion times, add them all together, divide by the number of boxes you've thrown down for a particular time, and divide by box area. That, by definition, is that mean. Okay? So this stochastic process has a mean. You allow the size of the box go to 0, and this becomes a field of densities in the same way that the Navier-Stokes equations are. All right? And you can actually do this for the bouncing billiard balls that are atoms in the atmosphere. The reason this is hard is that the transitions of the random variables are highly nonlinear. They depend on the resources that are created. For instance, just think about light. It's a highly nonlinear response to the presence or absence of a big tree overhead if you're in the understory. And those nonlinear transitions means that all the classical techniques that are used in physics to do this kind of moment upscaling don't work. Okay? So I was on a 20-year, mostly ineffective campaign to try to discover ways to do this correctly. And I wrote hundreds and hundreds of pages of computer code that don't work, and derived, volumes full of mathematical derivations that are now stranded assets and useless. And one day stumbled across this thing that we call the ED approximation now, and is the underpinnings of the ED model. And it's really quite simple. If you're a statistical physicist, you'll understand this, and if not, you just bear with, right? What you want on the left-hand side is the mean, the expectation of the random variable in a particular spot. And on the right-hand side, what is represented in a stochastic process is all the possible transitions among the random variables. And so a particular spot could gain a new tree in it of a particular size if it was born in there. It could gain a new tree of a particular size if the tree was already there and grows into that size. It could lose a value by getting grown out of or by that tree dying, and so on. So there are all these transitions, and they all depend on their neighbors, the neighboring states of all the random variables. So one of the things that physicists do is just say, screw it. I'm just going to substitute the mean for all those random variables, build a mean field model, and hope for the best. Mathematically, that's formally equivalent to doing a first-order Taylor expansion about the means. And you can derive equations from that, and blah, blah, blah. And it works if the variances in the transitions, the variances are sufficiently small, if there aren't sort of nonlinear things happening across a variability. And this demonstrably doesn't work for these forest models. So if you actually do that and build the mean field, it falls apart. And it falls apart for a simple reason. The understory light intensity in the simulation I just showed you is shown here at a particular place. That's the mean value. There are a whole bunch that are underneath that mean, and a few that are wildly over it. And these are the ones that are responsible for regenerating the canopy. And without them, the system falls apart. And so one day when I was running around, it occurred to me that if we simply calculated a conditional mean, conditional on a death of a nearby large individual. So it's formally possible to say, instead of calculating a mean, I'm going to calculate a mean conditional on some event. And this is conditional on A years since some tree above a threshold size died within some distance. All right? And so this is simply showing, if you calculate that, what's the understory light level conditional on the age since the last nearby disturbance. You can see all of a sudden that the variance conditional on that time is now very small. And so if we calculate the mean field of that using that conditional expectation, we end up with the ED model. And the ED model also goes through the data, if you're predicting above bound biomass, and it goes through all the stochastic simulations correctly there for 3 species. That's from the original paper this is a figure that Moorcroft and Hurt generated when they were students in my lab ages ago. And so you can actually then derive formally these integral partial differential equations, which is known as the ED moment approximation and is the basis of ED2 and everything else. Now the problem with ED, the nice thing about ED is that it actually works. You can put the same parameter values in functional forms from a simulator into this thing, and you usually get the right answer, get the same answer that the simulator produces. So in that sense, it does the upscaling correctly. It takes individual level information, and it turns it into community level prediction without simulating the individuals. The problem with it is that it's analytically intractable. You can't solve the thing with a pencil and paper. You still have to do it with a digital computer. One of the things that that original ED work did that turned out to be useful, that a lot of other people have used, is that it introduced into one of these models for the first time a continuum of species. Here's a bunch of different leaf traits. You have a bunch of different generic plants that differ from one another in some continuous way. And so when you decide how many different kinds of plants to put into a run, you just break up the continuum. Because physicists count for a reason 1, 2, 3, infinity. Once there are 1,000 species there, it's probably better to have a continuum than to have 3 or 2. All right. So we did use a continuum of species, which helps, but still, it wasn't enough. So the thing I want to leave you with from this part of the talk is that my group also designs the ecosystem component, the land component of NOAA's GFDL Earth system models, and has done for a long time now. And so we had the ED model going in our lab when it was still gathering absolutely no citations for about a decade, right? And we decided not to use it as the basis of our Earth system model, all right, as our land model. Now, subsequently, just about every group in the country, and a lot of them in the world, have the ED model, or an ED model under development as their land model. Everybody but us, all right? And actually, we've added the ED moment approximation to our model recently. But the important point here is I want to leave you with the why of that decision. So we built a model that excluded all that fancy schmancy stuff, but included a very, for the time, advanced parameterization for land use, secondary successional forestry, and some things that we thought we understood. The reason we didn't do it is that we couldn't do analytical calculations on something that had the capacity for very complicated behavior. And we thought we'd never get it to work because we thought unexpected things would happen. We wouldn't be able to diagnose and understand them, and we would just spend a very long period of time frustrated and not making any progress. All right? And so we moved on. I moved on to looking for another mathematical approximation that was better behaved. And so one day we got to, and so we did the sort of time-honored thing of we added complexity to the model to try to make it simpler, right? And one of the first things we noticed was that, like in a lot of these forest simulators, unless you do something sneaky, they make these raggedy canopies. The trees don't get out of each other's way in the right way. And you know, with gas exchange, you really kind of want you want a good blanket, like you can see out there, right? And so we did a lot of flying around in helicopters and taking stereo pictures of canopies. This is from Stephanie Bowman's work from Barrow, Colorado Island in Panama. And eventually came up with this tessellation scheme that I'll show you here, but one of the punchlines on it is that then we discovered it in the literature from 1967, and it turned out to be like the thing that every forester knew to do, right? Anyway, the idea was trees have a characteristic crown shape that is the way a tree looks like if it's, say, growing in a park, all right? Maybe growing in a park with few nearby trees so that it's nervous about them. They sense the far redshift. But then, you know, the carry branches quite a ways down, right? And you put all these together, and the rule is that whoever's got the highest foliage wins. So you trim the canopies this way, okay? And from above, that causes the canopy to tessellate with these little mounds, right, like that. They make these tessellated territories. That's formally a mathematical operation called a tessellation. And the theory of random tessellations is not for the faint of heart, all right? It's even worse than the other problems I've talked about. Physicists work on it a lot. Don't go there. There'd be monsters, right? So this was like taking everything in the wrong direction. We knew it. But beyond that, the tessellations look a little funny. They're all kind of elongated, and I don't like the way they look. They don't look like trees. And so part of Stephanie's work was to connect where the canopies were to where the stems were. And what we discovered was that most stems were underneath their neighbor's canopy, and most canopies then were over their neighbor's stems. The trees move around as they grow. And there's a population in any one spot of at least 10 canopy trees that could be anywhere, and they've jockeyed for position. And so what happens because of this phototropism, this response to where plants grow towards light and creates this thing? On average, a tree in a tropical forest is leaning 10 degrees, which given the height of the tropical forest is enough to have its crown over its neighbor, not over itself. Okay? So imagine that you have a tessellation here, and these things are the crown join heights of trees that are differentially spaced. And you can see that they're quite variable. If they're nearby, the crown joint height is high. If they're far apart, the crown joint height is low. Now let's suppose they all lean away from one another if they're close together. And that causes this crown joint height as they lean apart to drop. See? The number's small. And if they're too far apart, so they tend to lean together, that causes the crown joint height to rise. So the phototropism reduces the standard deviation of the crown joint heights. And this immediately sparks the mathematician in you to say, well, maybe there's an approximation where that crown joint height standard deviation could go to 0. But is that a reasonable thing to do? So we did all kinds of simulations. This is for 2.5 degrees of lean. And 2.5 degrees of phototropism that leads up to 2.5 degrees of lean more than halves the standard deviation of crown joint heights in one of these models. And so that you can show that realistic levels of crown joint height standard deviation of phototropism lead to crown joint height standard deviations that are more than an order of magnitude smaller than the mean and well within the range in which you could approximate things. I'll skip this slide because I'm getting ahead. And so we could take the approximation, which we now call the perfect plasticity approximation. What happens if plants were so good at partitioning the canopy that they could make those crown joint height standard deviations 0? And let's then take that to the forest inventory in the US and say, can we predict who's a canopy tree and who's not a canopy tree based on that, right? So the way this works is the tessellation happens, the canopy trees fill the canopy. There is also understory trees for which there is no room in the canopy. They're too short. The thing gets filled up by taller trees. And we want to just say who's a canopy tree and who's a sub-canopy tree. That's the rule. And we do this with inventory data from stem maps, and it's millions of trees in this case in the forest inventory. We did it for 189 species, and these are predicted in actual, and the answer is yes, we can. All right? We can predict which species are in the overstory and which ones are in the understory with a high degree of fidelity using this method. And the niftiest thing is, from my standpoint, or one of the nifty things is that this model, if you want to use that same method that I talked about, is possible to solve. And it's possible to show that under that perfect plasticity approximation, this thing reduces to this set of integral partial differential equations. All right, so that's a mathematical operation. So these equations are the correct scaling of that thing when the phototropism is big enough to drop the crown joint height standard deviations. And so this is a set of runs of the model with the perfect the stochastic model with the perfect plasticity approximation used to predict canopy versus overstory, and the partial differential equations, and they're all on top of one another because the model works. All right. So the other thing about this perfect plasticity approximation is after 2 years of developing the mathematical methods, it's possible to solve this thing for important cases all over the place analytically and get solutions. You can get coexistence criteria, successional sequences, size distributions in old growths. You can calculate all these things with a pencil and paper now. And so you finally have what I was looking for in the ED model, something that I could interrogate to help me guide and diagnose what went wrong when I'm designing a land surface model. All right? Okay. So we also took the partial differential equations that came from this to the forest inventory to see if we could actually predict succession. And I have one example here that comes from a paper we published, and a couple of papers we published 8 years ago. And in this case, we took individual vital rates from the forest inventory data, and then we went and got stand chronosequences that covered 100 years of successional change that we tried to predict. And this graph shows the change in basal area, so that's an increase and that's a decrease, over 100 years for a bunch of different species, in this case in the lake states, Minnesota, Wisconsin, and Michigan. These are for mesic soils. It's a particular soil class, do it for all the different soils. And you can see the predicted and the observed, and that's pretty good, right? So those partial differential equations are in fact predicting the transitions that had been observed in nature for the right reason. Okay, so now I want to talk about what we've done with this thing since that time. I'm going to give you a couple of examples. I'm going to start with the fate of the carbon sink. You all know that the atmospheric fraction is been about 45% roughly for 50 years, right? Bounces around all over the place with ENSO and other things. But 45% of the CO2 we put into the atmosphere actually shows up in the atmosphere. The rest gets eaten by the oceans and the terrestrial biosphere, which are gaining weight, all right? And the question, and so there are many people that have tried to look at the fate of this carbon sink. I was a part of a paper that I actually don't fully believe at all. But anyway, that said about half of it's due to CO2 fertilization, the other half's due to land use change. The land use sink will eventually disappear as the forests recover, right? Land abandonment, the forests recover. But what about the CO2 sink? CO2 fertilization sink, will it diminish through time? And most of the thinking on this follows from a paper, important paper by Hungate et al. In 2003, that fundamentally views the world through Liebig's law of the minimum, or as one of my postdocs calls it, Liebig's law. You've probably heard that. All right, Liebig's law of the minimum says whatever resource is in the lowest supply is going to determine productivity of the system. So in this case, this barrel is from Liebig's sales promotional material, and I give magnesium and nitrogen, and the lowest stave determines the water level, right? He was sued. You know, the guy was a charlatan, it turns out. All right, in any case, he was a fertilizer salesman. So Hungate said, look, here's the amount of carbon that we predict from the early dynamic global vegetation models as a result of over the 21st century because of increased atmospheric CO2. And here's the amount of nitrogen that will be required if there's no change in the stoichiometry. And so these are for different models at the time under two different assumptions. And this is the limit that Hungate et al. Thought the nitrogen cycle could supply. And the answer was the ecosystem was going to run out of nitrogen. And the sink that has been mitigating so much of our folly at filling the atmosphere with greenhouse gases was going to disappear. And we were really in trouble, right? And it hinged, of course, critically on this C to N being immutable. If the C to N went up, then you wouldn't need any extra nitrogen. If it went down, you'd need more, right? So when you look at the physiology of nitrogen use in its simplest form, right? The most common enzyme in the world is rubisco, carbon fixation. And it's a catalyst, and the Le Chatelier's principle applies. If you put more CO2 on this side, you get more carbohydrate on this side. And even if this doesn't go up, if that goes up, the carbon storage goes up, right? So from Le Chatelier's principle, as opposed to Liebig's law of the minimum, you might not expect nitrogen shortage to result in a diminished sink because this catalytic activity still happens. The reactant is more common, so that the product should be more common, right? And that will require, though, that the C to N ratio in the vegetation is capable of changing, right? If that reaction is going to continue to go that way. So we first tried to predict what plants ought to do. So we've built an Earth system land model that is the new version at GFDL is called LM4. We name them really, imaginatively. Land Model 1, Land Model 2, Land Model 3. Now this is 4. We also have OM1. Guess what is it? Ocean Model 1. And AM1, AM2. Okay, so this thing has a universe of possible species, and you can that vary along a continuum. And the one I'm going to be showing you here is just how much photosynthate goes to leaves, fine roots, and stem. Those are the only variables we're going to be considering here for this first analysis. And then there's the usual set of things. And we think these are trees or plants. You can configure these so they're grasses or whatever you want them to be. And you put them in competition with one another. And we can think about this as being in a plant simulator. And what we want to do is to compete all possible of the infinite number of strategies against one another with and without enhanced CO2 and find out who the winners are for the most competitive plant under different conditions. That's a Nash theoretic or competitive optimum. And of course, there's not enough computer time in the world to compute an infinite number of things together with 3 trillion canopy trees. And so we do it with these equations and using the calculus of game theory to derive the winner analytically. It's the only way you're able to do this sort of thing. So that's what we do. And the way to think about this, the way I think about this, is at 0th order, the decision that's really going to have a lot of materiality is whether or not the plant builds the productive parts of its, if it uses the carbon dividend to try to build the productive parts of its physiology, the leaves and the fine roots. But you can think of them as improving, optimizing a consumer electronic or something like that, something useful, versus optimizing the wood weapon, which is like building a weapon. So what should it use its carbon on if it's to be more competitive in a CO2-enriched world? And the reason this is so material is that if you build it into wood, this is, first of all, an N-pore tissue. It's fundamentally unconstrained or less constrained by nitrogen, 500 to 1 carbon to nitrogen ratio. Right? If you build it into leaves, those are really nitrogen constrained. And if you build it into fine roots, it's intermediate, but closer to leaves. Also, the leaves and fine roots are short-lived. If you double the rate of production of a short-lived tissue, you get a sink for 1 year, 2 years, and then it's done, because the sink saturates as the same number are dying as are being produced. If you double the rate of production of a long-lived tissue like a forest, you get 100 years of amplification for that sink. So that putting the carbon into this, the long-lived tissues, will result in 100 times the weight gain as putting the carbon into this. So it's the difference between a big, long-lived sink and a short-lived, small sink. So the way to think of it is the Nash optimum, where you're thinking, what fraction of the carbon dividend from CO2 fertilization should I stick into the wood weapon, which gives me a great big sink, and what proportion over here, which will give me a failed sink? And so I want to answer this question under different inherent nitrogen mineralization rates. Now, before doing so, I want to say that we didn't just trust the model blindly. We first said, well, instead of a CO2 fertilization gradient in productivity, let's check the calculation out against natural gradients in productivity and find out whether or not the allocation decisions that plants make across geographic gradients in productivity match the predictions of the models. And so these are all the data we could find, which is a lot. These are all different forested sites at all different latitudes. And this is the fraction of NPP going to fine roots versus foliage, fine roots versus wood, wood versus foliage. The dominant ecological theory focused on a trade-off between foliage and fine roots. Thought there would be a root-shoot trade-off. It turns out the data say no, the trade-off is between fine roots and wood. It's the weapon versus below-ground resource gathering. The model predicted the black lines with the productivity gradient going this way. Those are the data, and you can see we did a great job, okay? This is not what we expected, and it's actually what was observed. So we had some reason to believe this model's opinion about the response of vegetation to a change in productivity. And so we did this analysis. It's published in here. You can read about it a year and a half ago. And the answer is, especially when nitrogen limitation is severe, plants are faced with a carbon dividend. Liebig's law of the minimum would say, I'm going to have to throw it away. I can't use it for anything. A competitive plant says, you know, I can make wood out of this and kill my neighbor's children with it. And they elect to do the latter, all right? And so incidentally, you can check the prediction of this model. And so in other words, we predict that the sink gets exacerbated by nutrient shortage, not diminished, all right? And is maintained under mild nitrogen limitation. And we did an analysis of the face data, the free air CO2 enrichments. And in fact, we're able to predict what was observed in the face data. We actually had to build a different below ground model to predict the half that was due to what looks like priming, but that's a separate story. So you can read about those papers. Incidentally, we get the opposite conclusion for water shortages. Our model predicts that water shortages will be downregulated, will downregulate the carbon sink for interesting reasons that I don't have time to talk about. I'm also going to skip this. This was the actually showing that we get the same answer from our Earth system model, so we understand why the Earth system model is doing what it's doing. Okay, I'll just go past this. I want to move on to this rainforest business because it looks like I've only got 10 minutes left. Yeah, I want to leave some time. So I want to talk about, because I know a bunch of you are working on tropical stuff now, and so I want to talk about the cause of the mysterious rainforest power law, because it turns out to have carbon cycle implications. And this is a paper that we published in Science. Caroline Ferrier, who some of you know, is a coming rock star. She's at the National Institute of Mathematical Biology at Oak Ridge right now, but she's starting an assistant professorship in the fall at UT Austin. And so Caroline actually showed that the explanation I'm about to offer you is correct. In my view, it's an extremely convincing demonstration. I figured out the mechanism after a challenge from Caroline, but it would have just been another story without her extremely insightful and difficult data analysis. So the phenomenon that is of interest is this set of power laws, which gives the diameter of a tree and the number of the individuals in a bunch of different rainforests. And this is from a paper by Enquist and Nicholas in Nature in 2001. And the exponents are almost all 2, -2, all right? So -2 power laws all over the place. And these are extremely tight power laws for something as messy as a rainforest. At Barrow, Colorado Island, which is this 50-hectare island in Panama that the Smithsonian runs, the most studied rainforest, I think, of the world, you've got extremely good census data, and the blue dots mostly contain their error bars. There's so much data. And there's the power law best fit. And you can see just how remarkable, I mean, this is not like a messy pattern. It's 1,000 species. You go into the rainforest, it's like a mess, and yet there's this -2 power law just emerging and looking at you. And every rainforest you go into, you look, and there it is, right? And so why, first of all, should a global modeler care? And what I want to leave you with is, even if you're just interested in like the global carbon balance, you should care about this power law for 2 reasons. First of all, tropical forests store twice the carbon per hectare as temperate forests. Half of the excess is in a few big trees. And we actually understand that. We understand it all too well. Our models outproduce these things, right? But when we tame them right, we can predict these easily. It's simply due to the fact that there's year-round growth. And so trees grow faster. And if they live to something like close to the same age, you get some big trees. And those few big trees are responsible for half the difference between temperate and tropical forests, right? The other half, though, is the power law. It's all that stuff in the middle. If you fly in a helicopter over a temperate forest, say in the eastern part of the US, a mesic temperate forest, and drop a plumb bob out of the helicopter, it will hit on average, pass through on average, 1.2 canopies before it hits the ground. There's a canopy, usually you hit, and then there's sometimes, a fifth of the time or so, you hit an understory canopy. If you do that on BCI, you hit 3.6. There's a canopy, a subcanopy, a sub-subcanopy, and then most of the time you hit a sub-sub-sub-canopy. And this is true everywhere in the tropics. It's what you see when you walk into a tropical rainforest for the first time. You say, what is all that stuff? That's the stuff in the middle. And that's responsible for a large fraction of the tropical carbon storage, and it just doesn't have a temperate analog. So what's causing that thing? It's extremely regular, it passes our test. Boy, I bet it has a simple explanation. What is it? So the first thing to note is that there had been a lot of explanations proposed. People had run conferences, there were fights back and forth in the literature. Enquist was on one side, Caroline Ferrier and a bunch of people were on the other side. And all of their explanations were equilibrium explanations. They were all explanations that would have these things cause, if you knock the forest down, this power law would assemble slowly and lock in. In my view, none of the explanations were, none was both parsimonious and plausible. There were parsimonious explanations that were completely implausible, and unparsimonious explanations that were so complicated that they were almost the same thing as the phenomenon, but nothing in between. And so the first thing, well, actually the first thing we did was figure out the mechanism, but the first data analysis that was really critical was that Caroline went and said, let's look at the transient dynamics of the assembly of this thing. Because in BCI we have 30 years of data, and we can look at places that have been knocked down, and we can watch this thing assemble. And so there's 0 to 5 years after a big gap forms. The gray is the error bars for what it should be if it were following a power law, okay? So this is a statistical thing that's defensible. You can look in the original paper. So if it's a power law, it's inside the gray. These are different size classes, and these are deviations from the power law. After 5 years, more size classes are starting to climb in. By 15 to 20, they're almost all in, and then they're all in at 25 to 30. So this thing is clearly assembling from the bottom up, filling as it goes. But then if you look, well, what happens afterward, greater than 30 years? The answer is the big size classes fall off. So this thing turns out to be a transient that starts to decay away, gets built up during succession, and then it starts to decay away. And what we're looking at when we look at that power law is the ghost of many, many successions past. All right? So what's the explanation? So it turns out that if you actually analyze what's causing it, it's the crystalline distilled essence of the assumptions that underpin ED and the PPA working together. It's only those things. You need almost nothing else, and I want to show you that now. So first of all, it's all about succession, so you need a successional mosaic, like in ED. Places where the canopy gets knocked down by a microburst from time to time, and then it regrows again, and that's the basis of ecosystem demography in the ED model, as I showed you earlier. And so we took the rate of this from Central Amazonian remote sensing, because it's the only place we could get enough data, right? Can't do it from BCI, but you can get enough data over the Amazon. So that parameter we took from that. Second, within each place after it's been knocked down, the PPA operates. So seedlings come in and saplings that are residual are there. They grow up. They form a canopy that they partition. As they get bigger, individuals get smushed into the canopy because there's no longer any room for them, all right? So that's what the PPA is all about, right? And so that's it. That's the whole model. There are 5 vital rates: the growth rates of trees in the canopy, the radial growth rates of trees in the understory, the mortality rate of canopy trees, the mortality rate of understory trees, and the annual new saplings produced by a canopy tree per unit crown area. Those 5 parameters are taken from the medians of the BCI trees across all species. Simplest possible thing. And then we have the crown area allometry, which turns out to be uber critical for these things. And the crown area allometry, the exponent is very close to 1, sometimes 1.1, sometimes 1, all over the tropics. We checked it in all the different CTFS plots. And I was actually working on models of why this is 1 on the plane out here. So I actually think I have an explanation for it now, but I'm not even sure of it. Okay, so when we put that together, we get a prediction. And the prediction in this case is the gray. And the blue is the data. Okay? And you see how well this is not the kind of prediction I'm used to in ecology. We predict every single size class exactly, okay, when you run this thing. Every single one. These are deviations from the power law, including these deviations at the high end. Okay, so the crystalline essence of the ED and PPA approximations collectively predict this thing, this size structure, and essentially perfectly with the simplest possible demographic vital rates. Really astonished me. Right? Never would have expected that it worked that way. And beyond that, the slope here turns out to be 1 plus the crown area exponent. All right, so empirically, if you change that, that slope is 1 plus that exponent. Now, why is it 1 plus that exponent? What's going on here? Got a little math thing here, and that's going to finish it because I'm out of time. Crown area exponent here, the crown area is a constant times the diameter raised to a power, which is close to 1. A gap area is P, And since the PPA says, well, the saplings just divide up the crown, the total gap area. That's what they do. It's just that simple, right? This crown join height standard deviations are 0. And also because fecundity is high enough that the individuals that tend to be in the, think of a swarm of saplings growing up, fighting to get into the canopy and stay in the canopy. The biggest ones all tend to be about the same age. They're the ones that got there first. So they're all close to the same size, like is shown here. So the number of individuals in the canopy at diameter D is equal to the gap area divided by the individual crown area, right? Just because you have to say, well, how much room is there for one? Well, how big is one? How much area is there? And the ratio is the number. So that's the number of individuals in the canopy at the time when the canopy has diameter, stem diameter D. And then if you say, well, how many are deposited in the understory at diameter D? Well, the number that are deposited in the understory are the ones that get squeezed out the way this poor guy did from the overstory. And so that's minus the derivative of the canopy individuals with respect to diameter, which is this relationship here. It's just the derivative of that thing with respect to D, which, if you remember your calculus, has the exponent theta plus 1. This is a theta plus 1 power law, which is a minus 2 power law. Okay? That law there says, since theta is 1, I am a minus 2 power law. So it's simply that process, the PPA squeezing individuals into the understory because of the demography, the combined demographies of different successional ages from the ED approximation that creates the minus 2 power law as a sort of fundamental structural thing that flows out of this. And we've actually checked this. There's small variation in theta. Sometimes it's 1.1. And where it is, the power law size distributions are minus 2.1. All right? And where it's 1.0, they're minus 2.0. Right? It explains all the little wiggles. So my message for you people is make sure you get ED and the PPA right, or you're not going to predict tropical size distributions. Right? Okay. So I had another one here, but I'm going to go past it and finish off. So the take-home messages are scaling from tissue to individual to population, community, ecosystem is something for which we now have some defensible tools. All right. So in my view, the field, for me, this is enormously gratifying because when I was many of your ages, I just didn't know if this would ever happen in a college. And it's really quite nice to see a theory developing that might be used in anger more and more. Secondly, will nitrogen shortage stop the carbon sink? My prediction is no, because the most competitive strategies are going to use the excess carbon for wood the way, and that was one of the dominant responses in the FACE experiment. It seems to me you're going to use it for something. But that's a prediction, and unfortunately we're running the experiment. We're going to know. And third, what's the cause of the mysterious rainforest power law? The answer is the perfect plasticity and ecosystem demography mechanisms. And the last thing I didn't tell you about, and so I'll take questions. Yeah. No, so here's the amazing thing about that. So I always thought that the explanation had to be something like this. If you look at it, this thing doesn't depend on any disturbance rate, any growth rate, any death rate. It depends only on, the only dynamical dependence is this crown area exponent. It doesn't depend on anything else. And this is why it's ubiquitous across rainforests that are on different soils with different productivity to get the same power law everywhere, because it turns out that power law doesn't depend on any of the vital rates we usually care about. It only depends on this structural parameter and is the result of optimal space filling by competing plants. So I'm not sure why those exponents differ subtly from rainforest to rainforest. I do know the calculations that I made on the plane coming out here indicate that that exponent is 1 because in the tropics, you grow extremely rapidly in height, and like 5 meters a year sometimes. And the game is to try to keep leaves on the top of your stem, because if you don't, your neighbor will, and then you get pushed into the understory and you're dead. All right? You're one of the 9,999 that die on the way up. And so that creates, because they're growing so rapidly in height, it creates enormous demand for nitrogen. Demand that far exceeds what a mature forest will, which doesn't have to build height as rapidly. And the evidence is that if you actually look at the demographies of leaves in these small size ranges, in these refilling gaps, leaves will live a month or less on species where they normally live 3 years. They've overgrown their leaves, they're recycling their nitrogen, trying to put it up, and so they're desperate for nitrogen to keep some leaves on the top of this racing stem. So if you figure out the mathematics of that, it turns out the amount of nitrogen you can deploy per unit height, which is a good measure of how much crown area you're going to have, you see, turns out to give you an exponent of 1. So I think it might have to do subtly with the nutrient status of different rainforests, but not in a way that affects growth rate in a simple way, but because it affects a structural parameter, a shape parameter. Yeah. Yeah, so they're fighting for light and water and nitrogen in our models, and soon phosphorus, right? But yeah, it's just whoever wins, wins. And the allocation schemes, there's an infinite number of different possible allocation schemes, and the best one wins. And then the question is, well, is that a plastic response within a species, or is it a swap in the species? And so we've done quite a bit of work. Ray Dubzinski, who's was the guy on the nitrogen work, the postdoc on the nitrogen work who now teaches in Chicago. He's done an analysis for a whole bunch of these different characteristics. How's that variability partitioned within and between individuals, species, within biomes, between biomes, cross habitats, all that sort of stuff. And to a first approximation, if you look at the species within a place, about half of the variation is actually within an individual. Individuals are enormously plastic in their allocation. If you think about the change in their C to N ratios and their harvesting of C versus N as they move from the understory to the canopy during their lives, the amount of N that they can harvest doesn't go up appreciably, but the amount of C they can harvest goes up more than a factor of 10. It's this huge change in stoichiometry of incoming stoichiometry they have to deal with all the time anyway, and their allocation responds to that. So about half of it is within individual, half of it is between. All of it that was observed, obviously, in the face plots was within. So as I was explaining to some of the people in some talks before, my group, GFDL, Elena Shevlyakova, who's the deputy director of GFDL and is in charge of the land modeling group, has assembled a large number of people working on nitrogen and phosphorus and microbes right now. And that seems well in hand, and leave it to the experts. And so I've just hired a whole bunch of water people, and I think there's some fundamental changes that need to be made in these models about how plants manage water. And so this is exactly the set of problems that we're going to be focusing on over the next few years. So I have lots and lots of ideas about it that I'd love to talk to you about, knowing what to do, right? And in fact, I'm even taking over at Eddy Covariance Towers management because of this, right? And so yeah, I recognize this. And so the answer is I don't think any of our models will predict water right yet, right? Just because I think we're missing lots in addition to taproots. Yes? Yeah, so what we do in those models is we've got a sort of a standard, century-derived carbon cycle and coupled nitrogen cycle. We've just swapped that out for something that's much more sophisticated but harder to parameterize, as we were talking about earlier. But in that case, it's like a century model. And we, analytically, we use what amounts to we use like a root finding algorithm to compute a pre-industrial steady state. And there's a periodic version of a Gauss-Newton algorithm, and we use that to equilibrate the below ground. And then we spin it up through the time that we want to do the experiment, right, which is the 20th and 21st centuries. Yeah. It's a great question. And in fact, I should just be ashamed of myself because I always say this, right? And I got going too fast. So what I said is true about the above ground, about the living portion of the carbon. What happens to the below ground carbon is, of course, a really interesting story. And if you have enriched C to N litter, all right, generally that's also going to mean a longer lived carbon sink below ground, right? I mean, all else equal, right? I mean, it's the expectation. If you had a guess, right? So my guess is that when you get a larger allocation to wood, it exacerbates the below ground sink. With that said, this is only one of two mechanisms that I think are necessary to explain the face model results. The second mechanism is probably microbial priming or something close to it, right? And as you know, with microbial priming, you could get the reverse. Right? So that mechanism actually can work the opposite way. Yeah? Yeah, like. Yeah, so we certainly do that, right? And the PPA gives you a particularly interesting story there where eventually you fall out of forest, right? So if you want to do it simply, let's suppose we do a fixed total ecosystem N, where the ecosystem model is just partitioning the N into different boxes, right? As total ecosystem N drops, you get sort of scrubbier and scrubbier and more open forest, and then it kind of falls off into non-forest, where the burden of the competitive prowess shifts really to below ground, right? In the limit, you don't care about your stem anymore. Right? Oh, absolutely. Yeah, so what we're doing now is with this LM4 model is we're taking every biome boundary and we're deriving analytically where we think it ought to be. And then putting it in the full-blown model, which includes, more complexity. And then it moves around a bit, or something surprising happens, and we figure it out. And eventually we get, we get that going, and then we move to the next one. And so the forest, grassland, forest, savanna, grassland, shrub boundary is we're just hot out. We think we have enough to do those now, and so we're hot after those. Yeah. It's really interesting that you say that, right? So this trade-off between, for want of a better phrase, risk-seeking versus risk-avoiding water use strategies is something I'm really preoccupied with right now. And I think that, so there's a very long story here that maybe we should take offline, because I've just cleaned out my whole postdoc stable and rehired all water people for this reason, right? And I cleaned them out in a nice way. They all got good jobs, right? They all went to permanent jobs. When I say cleaned them out, is I didn't like replace them with, it wasn't, every single one is happy. Okay. But I have cleaned them out. And I didn't replace them with a person like that. I replaced them with water people, physiologists, anticovariance people, hydrologists, and so on. And so I want to understand that continuum. And obviously, it has to do with balancing the risk of hydraulic damage and optimizing carbon in the absence of hydraulic damage. And so there's this long story here, and if I start talking about it, it'll be 12:30. Okay, so I think this is fascinating, and I have no idea. To the specific answer to your question, I haven't ever thought about it. So. All right, people, thank you.